So, welcome again, everybody. You've heard the name TANGO a couple of times. This is actually what it stands for, but I can imagine, yeah, you don't need to bother for reading it all. It deals mainly with combustion, with combusting systems, systems that are dealing with fire and burning something. So, yeah, it is TANGO, but of course this is not what we do in our research. About combustion, I can tell you that it's practically everywhere. So you have combustion at your homes, like in your home boiler systems, or yeah, fireplace. You might have some in your homes. Combustion is in transport, as you might have imagined. Yeah, a coal-burned train, for example, or a more sophisticated kind of type gas turbines in airplanes. Combustion happens inside, gas is being burned. And of course in cars, inside the cylinders there is combustion going on, things are being burned. Also it is an industry. In so many industries combustion is currently being used. For example, large industries like power plants, they have a scaled up version of a gas turbine in an airplane for producing power. Or in any other industry that needs to heat something up, like glass industry. So they have a furnace, they burn something, they make the heat. It is also used in entertainment. So could anybody guess how it can be used in entertainment? Firing something? No idea? How about fireworks? Yeah, here also you're burning something that has this color and you see it in a very beautiful way. It is also used in romance. Again, and give me some guess how it can use combustion in romance. Simply candles. In candles you're also burning something. There is a fuel being burned and combustion is happening. So when we say it's practically everywhere, it is everywhere. And it's very nice and very beautiful like this, but it can also go wrong. Like when a fire which is not under your control. So we want combustion unless we can control it, we can make use out of it. It could go wrong in many ways. It can go wrong in airplane engines, which of course we are all sort of afraid of. It can go wrong in our furnaces inside the houses if they're not designed well. If we don't do our jobs well, it might happen in home boiler systems. Or in many other cases like in car engines, or just simply when you're having a barbecue. It could just burn the whole thing. So one of the main things that can make combustion go wrong is combustion instability. This is one of the cases where it goes out of hand, that we don't want to happen. We want to somehow prevent it. And my colleague Luke is going to explain more about this part.
So thank you, Naseh. So in this project, what we want to do is that we get some more information. So, sorry, that we get some more information so we just can drive the car without this happening here. But I'm talking about combustion instabilities, and first I'm going to show a demo what this is about. So,
okay,
I'll move the stuff. So what we have here is just normal gas. We have a valve and we have a burner here. So we're going to...
Okay. Remember again, fire exit.
So at the moment nothing happens.
Yeah. It's all what it should be.
So this is then the combustion instability, and how does it happen? So it's an interaction between the gas flow, the sound which is also in the tube, and then also the combustion itself. However, as you can see, this is going to be very complex. That's why we need such a large cooperation, so we have so many different aspects of this combustion instability, and we have to research every aspect and try to combine all these kind of different phenomena. But then why should we do this? The idea is that we want to go to a greener future. However, we want to reduce the emissions from power plants. Furthermore, we also want to have that these power plants can operate dynamically. For example, if we build more wind turbines, there's no wind, so we have to put in more energy from the gas turbines. But then on a windy day, we have to reduce the energy from the gas turbines to have a constant level of total energy. And furthermore, we also want to use different fuels, like green fuels from plants and trees. However, that's where the trouble starts. It becomes really difficult to incorporate all these different aspects in one combustion plant. So how do we cope with this? And this is via research. And now Aswathy is going to tell about how we do this research.
Thank you, Luke. Hi, I'm Aswathy. So, as Luke said, how do you do this? I'll be explaining how we do research as a flowchart. So the first step in doing research is you identify the problem you want to solve. The second step is you gather data from the problem. So I'll just give you a simple example. Let's say I have a physical process and I have some data points like this. Some data points. Then I want to represent these points as a mathematical expression. Or in other words, I want to express my physical phenomena in terms of maths or equations. So I take these data points, I do some tricks, or then I try to construct a mathematical expression. That step is called modeling or mathematical modeling. So my first guess would be a straight line, just passes through this. So that becomes a mathematical expression to explain these points. The next step I do is prediction. I want to make sure the mathematical expression I got is right. So I use this expression, let's say it's called a function. I use this expression to make more predictions about my physical process. Let's say these are my predictions. But I cannot stop with this. I have to check whether these predictions tally with my physical process. So I do experiments. I collect data from these experiments. Then I compare with my predictions. So let's say these are my experimental values. So if you compare these two set of data, you can see that this function cannot represent these points. So I do the next step. Do they agree? Do my predictions and my experimental values, do they agree? If not, I'll do this cycle again. I'll gather more data. I'll try to fit, I'll model a mathematical equation. I'll try to do a prediction. Then I compare with experiments. Let's say I have a couple of points which agree with my mathematical equation and value. If they agree, then we explain our results to the world through conferences, by publishing in journals, or even events like this. So that's how we do research. It takes a lot of iterative cycles. And next slide, I'll show a couple of real-life modeling. This is analytical modeling. We have mathematical equations, things like that. Then you have simulations. Using the mathematical equations, you try to do simulations. And you compare with you compare with experimental data just to validate that you are getting the right model. So this work is done by the TANGO team here. So thank you for your attention. I'll hand it over to Maria.
Yeah.